What is weak convergence? Let N be a non-linear space and a sequence Xn in N is said to be weakly convergent to X if there exists some functional f belongs to n star such that limit n approaches infinity, f of xn is equal to f of x. So it means if xn is weakly convergent to x, then f of xn is convergent to fx for every functional, for every f belongs to n star, where n star is a dual space of n. So which n star means n star contains all of its functional. So first theorem is if xn is weakly convergent to x, then number one, the weak limit, x is called a weak limit. Weak limit of sequence xn is unique. Number two, every subsequence of a sequence xn converge weakly to x. Number three, number three, the sequence set of norm of xn is bounded. So this is very important result. Now we prove that. Now first part A. Suppose xn converge to x. It means weakly convergent. And also xn weakly convergent to y. We want to show that the x and y are equal because we want to prove that the xn converge to a unique limit. So by definition, limit n approaches infinity, f of xn equal to fx. Similarly, limit n approaches infinity, f of xn equal to fy for every f belongs to n star. Now from these two equations, f of x equal to f of y, it implies f of x minus f of y equal to 0. It implies f of x minus y equal to 0. For every f belongs to n star, it implies x minus y equal to 0. It implies x equal to y. Hence limit is unique. So it is a first part of theorems. Now B part, again xn is weakly convergent to x. By definition, f of xn which converge to fx. It means this sequence fxn, this sequence is convergent. So it is a convergent sequence of number. If it is a convergent sequence of number, then we know that every convergent sequence, every subsequence of convergent sequence is again convergent and has same limit. So it implies f of x and k converge to fx, where x and k is a subsequence of sequence xn. It implies x and k weakly convergent to x. So it implies every subsequence of xn converge weakly to x. Now third part, C part, since xn is weakly convergent to x, so again by definition, the sequence f of x in is convergent sequence of real numbers. Clear? So every convergent sequence is bounded, so it means it is a bounded. It implies f of xn less than equal to kf for every f belongs to n star. This k is a constant which depending upon a functional f, which depends on functional f. For different f, it has different values. So it means f of xn less than equal to kf, where kf is a constant depending on f. Now we take a x approaches to phi x be a natural embedding of n into n double star. Then for each n, norm of phi xn which is equal to norm of xn, and phi xn of f, which is equal to f of xn. Now, absolute value of phi xn of f is equal to absolute value of fxn. So this is by this equations. So this can be used from, so this is by this is by this values. So this is equal to this values. Now from that, so we know that this value, now phi xn of f is equal to f of xn less than equal to kf. This is by equation number 1. It means phi xn of f is a bounded set for every f belongs to n star. By uniform bounded principle, the norm of phi xn is also bounded. Norm of phi xn, which is equal to norm of xn. So it implies norm of xn is bounded. So this is by equation number 1. So this is again a very important result which contains all the three parts. After that, the next definition is strong convergence. Now, if we have a sequence in nonlinear space n and it strongly convergent to point x, then it means limit n approaches infinity, norm of xn minus x is equal to 0. So if sequence xn is strongly convergent to x, if and only if limit of this value is equal to 0. Next result is important, which implies that strongly convergent sequence implies weakly convergent. Or we can say that strong convergence implies weak convergent. But converse is not true. So first we take first part. Suppose xn is strongly convergent to x. Then by definition, that is written in equation number 1. Now, in order to prove the weak convergence, so we take for every f belongs to n star. N star means dual space of n. It means f is a functional. So absolute value of fxn minus f of x, which can be written as absolute value of f of xn minus x. This is because f is a linear transformation. F is a functional. So functional mean linear transformation or linear functional. So this values. Again, this can be written as less than equal to norm of f into norm of xn minus x. Now by equation number 1, as n approaches to infinity, this term approaches to 0. If this term approaches to 0, the left hand side of this equation is again approaches to 0. If this approaches to 0, then it means limit n approaches infinity, fxn equal to fx. It implies xn is weakly convergent to x. So every strong convergence is a weak convergence. So every strongly convergent sequence is a weakly convergent. So remember this result. After that, converse is not true. It means weakly convergent does not imply strong convergence. So it is again very important. So consider an example. Fn x, which is equal to sine n pi x in L capital L square on 0, 1 intervals. Now, phi of Fn can be written as integration 0 to 1 sine n pi x, sine n pi x, and sine n pi x hx into dx, where hx is a sequence integrable holds for every linear function of phi. Obviously, phi fn is the nth Fourier coefficient of fx relative to the sine n pi x. It implies limit n approaches infinity, phi of fn equal to 0. If this value is equal to 0, then fn is weakly convergent to 0. On other hand, norm of fn minus 0 whole square can be written in the form of integration 0 to 1 sine square n by x into dx, which is equal to 1 by 2. So clearly, this fn is not strongly convergent to 0. So we consider this example, which prove that Fn is weakly convergent to 0, but Fn is not strongly convergent to 0. It means weak convergent does not implies strong strong convergent. So which condition will be imposed to prove that weak convergence implies strong convergence? So that condition is finite dimensional space. So in finite dimensional space, weak convergence also implies strong convergence. Suppose n is finite dimensional vector space, norm space. If n is finite dimensional space, then it means the dimension of n is a finite. Dimension of n is a finite. And we can say that that finite value is equal to m. If dimension of n is equal to m, then it implies dimension of n contains m vector. Suppose E1, E2, Em are that vector. It means E1, E2, E3, Em are the basis of n. So this is a basis vector of n. If it is a basis vector of n, then any vector from n can be uniquely represented as linear combination of these vectors. So in this way, xn can be represented as linear combination that is written in equation number 1, where alpha I n are scalars. Clear? Now, let xn weakly convergent to x. If xn is weakly convergent to x, then by definition, limit n approaches infinity, f of xn is equal to fx for every f belongs to n star. Again, x belongs to n. So here again we write x in the form of linear combination of these vector e1, e2 and em, that is written in equation number 3. So from this, consider f1, f2 and fn functional. This is a sum functional which is in n star, which is in n star. So this is sum functional in n star, where fi ej basically Kronecker delta ij. When I equal to j, then the value is 1. If I is not equal to j, the value is 0. Now from equation number 1, we know the value of xn. So use this value in this equation, fi xn. So this can be written as fi linear combination of these vectors. Since fi is functional, so we can write it as in this form. In this form, by using the condition 4, in which when I is not equal to j, then this value is 0. So we find only one value, which is alpha I. So by definition of weak convergence, we know that limit n approaches infinity, fi xn equal to fi x. Now substitute the value of fi xn, which is equal to this value, and substitute the value of x. So we get this value is alpha I. From this, we find alpha in converge to alpha I. Therefore, norm of xn minus x, which can be written as norm of this values by using a triangle inequality. This value is equal to this values. Now, alpha in minus alpha I, this approaches to 0 as n approaches to infinity. It means the right hand side of this equation approaches to 0. It implies left hand side is also approaches to 0. Then xn is strongly convergent to x. So it means in the finite dimensional space, weak convergence implies strong convergence. And we know that in every space, strong convergence implies weak convergence. So it means in finite dimensional space, there is no distinction between weak convergence and strong convergence. When space is not a finite dimensional, then strong convergence and implies weak convergence, but converse is not true. But in case of finite dimensional space, weak convergence implies strong convergence and strong convergence implies weak convergence. Now question number 1. In Hilbert space, xn is weakly convergent to x if and only if the inner product of xn comma y approaches to x comma y for every y belongs to H. H is Hilbert space. Now first by definition of weak convergence, it implies this values. Now by Rice representation theorem, which is if f belongs to H star, then there exists some unique vector y such that fx is equal to inner product x comma y for every y belongs to H. Now substitute these values in this equation. It means f of xn can be written as inner product xn comma y and f of x can be written as inner product x comma y. So it means this inner product approaches to inner product x comma y as n approaches to infinity. So that is our result. Now, second question is give an example to show that weak convergence does not imply strong convergence. So that we already proved in previous articles or previous theorems. So independent, we can show that we can give the example to prove the weak convergence does not implies strong convergence. Next definition is subset M of norm-linear space N is said to be total set. So this is very important result. Total set. Total set means M is said to be total set if span of M, span of means linear combination generated by vector of M. Span of M, the span of M is dense in N. Span of M is dense in N means closure of span of M is equal to N. So which is a definition of total set. So this is very important. So next theorem is very important result. The statement of this theorem is if a sequence xn in norm space n weakly convergent to x if and only if it satisfies two conditions A and B. The sequence norm of xn is bounded that we already proved. Number 2, limit n approaches infinity, f of xn, which is equal to fx, for every f belongs to M, where M is total in n star. So remember, n star is dual space of n. So M is total in n star. Now first part, since xn weakly convergent to x, so we already proved this result. So we revise this result again. Then by definition, this is written as in equation number A. Now sequence fx in a is convergent sequence, and convergent sequence is bounded. So bounded sequence can be written in this form, right? Now we take a natural embedding x to phi x, which is from n into n double star. Then for each n, norm of phi xn is equal to norm of xn, and phi xn f equal to fx. Now absolute value of this value, which is equal to absolute value of this values, so again which is less than equal to kf by equation number 1. So it is a bounded set. Applying principle of uniform bounded principle, norm of phi xn is bounded. If it is a bounded, then substitute the value of norm of phi xn, which is equal to norm of xn. So it means the norm of xn is a bounded set, right? So which is a proof of first part A. Now second part. Since xn weakly converges to x, so this condition is true for f belongs to n star. Now since m is total in n star, then we can write it as in this form. Now equation number 2 is applicable for all functional f belongs to n star. By this result, by this result, span of m closer is a part of n star. It means this condition is true for span of m closer. Similarly, m is a subset of this set. So it means this condition is true for every f belongs to M. Clear? So simply, if any condition is true for India, then that condition is also true for Punjab. So it means uh, which we prove the result number B. Converse part, the equation A and B hold. So in converse part, A and B are given, or we want to show that the sequence xn converge to x, weakly convergent. Now from part A, there exists a constant k positive such that norm of xn less than k for every n. So this is equation number 3. Similarly, when n approaches infinity, norm of x less than equal to k. From B, n star is equal to span of M closer. For every F belongs to n star, it means F belongs to span of M closer. If span of M closer, F belongs to span of M closer, then it means there exists a sequence Fm in span of M such that this limit m approaches infinity, fm, which is equal to f, that is written in equation number 4. For given epsilon greater than 0, by this definition, there exists a fm belongs to span of m such that norm of fm minus f less than epsilon by 3k, which is written in equation number 5. Clear? So this value can be chosen as per requirement. Clear? So here we know that our requirement is epsilon by 3k. Otherwise, we left this space blank and substitute after our requirement. Limit n approaches infinity, fxn equal to fx. So this is by definitions. For every f belongs to M, so by definition, there exists a positive integer p such that norm of fmxn minus fmx less than epsilon by 3 for every n greater than equal to p, which is equation number 6. Now here f is equal to fm. Now let n greater than equal to p and absolute value of fxn minus fx. This term can be written as f of xn minus fmxn plus fmxn minus fmx plus fmx minus f of x. So by using triangle inequality, this can be written in this form. By using bounded function, the first and third term can be written as norm of fm minus fm into norm of xm, and third term is norm of fm minus f into norm of x. Now substitute these values by equation number 3. This can be written as epsilon by 3k into k plus epsilon by 3 plus epsilon by 3k into k. The total term is equal to epsilon. It implies when n approaches infinity, so f of xn approaches fx for every f belongs to n star, it means xn sequence is weakly convergent to x. So this result is very important. This is very important result. Clear? So very important result which contains if xn convergent to weakly convergent to x, then it satisfied A and B condition. If A and B condition are satisfied, then it proves the xn is weakly convergent to x.